Hi, this is Professor Cummings, and I want to bring you another video. Again, I'm still going with this theme or this series of videos on kinematics. This is really part of a bigger class on machine design, and just showing how the kinematics of what you learn in your actual kinematics class gets applied to different mechanical devices, mechanical elements. So what we have here is a discussion on the tangential versus angular motion. Right, and again, this has been, again, still following that same series. And we have here a couple of equations that I wanted you to understand. And, you have this S stands for displacement. So, and that's translational or tangential displacement with respect to time. The derivative of that with respect to time is equal to, if we were to convert this to angular rotation, it would be the radius of your rotation, and that's the differential theta in radians with respect to time. So r times theta, that's going to be an ongoing theme with displacement, angular velocity, and angular acceleration. So that radius times that angular velocity, or change in theta with respect to time, is what converts to tangential velocity, and that is actually equal to angular velocity times that radius of the same rotation, or the same center of rotation or travel. So again, you can see that, like I said, the radius times the angular displacement of theta is equal to the velocity, and that is equal to the tangential velocity times the radius times the angular velocity. And you also have your angular acceleration times the radius is equal to your tangential acceleration. And then you've got something called the normal acceleration, going inward into the turn or inward into the radius, and that is angular velocity squared times your radius. So tangential and angular velocity is related through the radius of motion. Right? So again, tangential and angular velocity are related through the radius of motion. And this is where you have those common equations. So just looking at this in terms of the two gears, you get two different gears. They're in mesh, and this gear, which has a clearly smaller radius versus the other gear, and it doesn't matter which one is driving, which one is driven. All I want you to really pay attention to the fact is they are enmeshed, and they have two very different radii. But one thing, because of these equations, we know that one thing they have in common is a common tangential velocity. So where they meet, that is a common tangential velocity that is proportional to the radii of gear A and gear B. We call it the smaller one gear A, larger one gear B. So the tangential velocity between these two are the same, or is the same, but they have a proportional angular velocity, how fast this rotates in radians per second. And this versus the B rotates in radians per second. Those will be proportional to the radii. So then this is just the nature of gears, where they have these common tangential velocity is because of where they mate. Now, if we look, and there's your common tangential velocity. So tangential velocity of A is equal to the tangential velocity sub B. Now, when you have an example, say this could be two pulleys with a belt, or this could be two sprockets with a chain. What you have here is still the same sort of concept. A common tangential velocity via the belt or the chain. And the radii also dictate the angular velocities. That would be omega, just like in the two examples. So again, in this case, your tangential velocity between A and B is your belt. So when you have a belt system, two belts on your, like I said, the chain on your bike, or two pulleys with a belt, you have the common tangential velocity that's going to work between the two problems VA and VB, will be common. And the rotational, the angular velocity, will be proportional to the radii of both of the pulleys, between the two pulleys. Now, you have a situation like this. I got this GIF of a compound gearing system. And what I really want you to pay attention to are the blue and the yellow gear. So when you look at gear A and gear B, they actually share an axis. So they have a common axis. They're not in mesh with their teeth, and they're not in mesh or in alignment with a belt. B connects to the green and A may connect to the red, but A and B are connected by a common shaft. What that does is it means A and B actually have a common angular velocity of omega. They have very different radii. Radius of A is clearly larger than radius of B, but the angular velocities between the two, if you were to track the teeth, just pick a point on there, you'll see that they fall in line with one another. So the angular velocity is the same, but in this case, your tangential velocity is proportional to the radii. So here you've got a common angular velocity. They have the same center, and they rotate about that center at the same rate of radians per second. So what you're getting is a tangential velocity, which is what's going to mate with this red gear from A and this green gear from B. Those are the tangential velocities, or that's where the tangential velocity will manifest. Those are going to be proportional to their respective radius. So when you look at this concept, this is where the whole idea of gear ratios or velocity ratios, the same thing, actually comes from. It's based on this equation here. Let me just turn this into a pen, and we will take it here. This equation here. You can see that shows up as a theme, a running theme between here. A little bit of algebra is different, but same equation. All right. So you can see when that equation stays put, it just comes down to when they have a shared tangential velocity, either through example, the one with A and B in mesh, or a shared tangential velocity because of a chain or a belt, or a shared angular velocity because of a common shaft. It dictates, whatever one is common makes the other, proportional to the radii of the two. So now let's look at this other example. So another problem that keeps coming up, or a part of this sort of mechanical design problem that comes from kinematics, is the whole idea of your constant acceleration versus your acceleration as a function, right? And this would be, you'll see this a lot with problems with things that are falling for constant acceleration. And when things are acceleration of a function, might be some sort of known function that is going to usually have to be given to you, or maybe something that's being designed like an engine or something. And down here you have a few diagrams, one that represents uniform motion, one that represents a motion with a constant acceleration. And here we have a displacement, velocity, and acceleration for both sides. Displacement, that's shown in meters, velocity, and acceleration. Three graphs basically showing that these things run into alignment with each other, and your x-axis in this graph is time in all examples. So basically you're looking at a body in all three of these graphs, or excuse me, all six of these graphs. Three graphs for uniform motion, three graphs for constant acceleration. And when you look at these three graphs, what you're doing is you're graphing, what that displacement is with respect to time. And here, what you see when you've got the constant acceleration, you do it with a parabolic graph, and that would dictate, what's going to go on with your velocity and your acceleration. And the way to understand that is with another concept that is true in a lot of your mechanical engineering, particularly in your mechanical designs, but your kinematics, is this concept of being able to use calculus, derivatives and integration to go from displacement to velocity to acceleration and back again. So when acceleration is presented as a function of time or some other variable, displacement, and velocity can be found. So here you have the integration of velocity is equal to, the integration of acceleration with respect to time, or this particular equation. Acceleration is the derivative of velocity with respect to time. And the same can be said working backwards to displacement. Velocity, that should be displacement, is the derivative of displacement with respect to time. So this equation here should have been up there. Now, when you've got constant acceleration, it's not necessarily a function, it's the four kinematic equations come into play. So when acceleration is constant, there's a uniform velocity, and the four kinematic equations can be applied. So that would be in this example here, these three graphs here. And these are, I'll have a video where I go through how these equations are derived in my kinematics playlist. And I'll put a link up for that so you can see that at the end of the video. But what I want you to notice also in this is that your displacement, here you got your translational displacement and your radial displacement of theta. The equations are otherwise, very analogous to one another in all examples. Here you got tangential again, and this is equal to your initial velocity times time, plus 1/2 your acceleration times time squared. Over here, you got your another change in your displacement, radial displacement this time, and you got angular velocity, initial angular velocity times time is equal to 1/2 the angular acceleration times time squared. And you can see this goes all the way through. The same four equations play out both translationally as they do for rotationally. So I just wanted to put that video out there to continue on and I'm showing how this applies to mechanics, or machine design. So how these mechanics apply to machine design. And I'll be making, again, more videos, probably twice a week, I think is a schedule I'll be sticking with while we have this semester. So again, leave any comments, anything you want me to clear up or clarify, and I can try to work a video for this. And we will, I'll talk to you next time in the next video.